Make me a co-host.
Are you inside? Yeah. Okay. Hello, everyone.
Hi there.
So it's really a pleasure. Just a second, my co-host. Yay! It is super exciting to see all of you here. So my name is Clarice. I am faculty here at UCLA, and I'm here with my co-instructors. Please introduce yourselves alphabetically. Abasalt, introduce yourself real quick.
Hello, my name is Abasalt. I did my PhD in quantum physics, and now I am a postdoc at Quantum Biology Lab with Clarice.
Yeah, then there's me. I'm Alessandro. I'm also a postdoc here at the Qubit Lab with Clarice. And yeah, that's pretty much it. And Natsumi.
Hi, everyone. My name is Natsumi. I'm also a postdoc here at UCLA.
So we're super excited to have you all of you with us into this first possibly quantum biology, right? So today this class doesn't require any prior quantum or quantum biology. We'll be learning together. So, one can attend. This class is also attended by a bunch of UCLA undergrads, but also by people, undergrads and high school students and other people all across. Happy to have you here. Today, we're going to start with a introduction to quantum mechanics class. And in the following, we are going to be talking a little bit about quantum biology, which is whether whether nature might be using the law to function and to function optimally. So in the next weeks, we will be going over one chapter of this book at each time, okay? So please, this is a book that talks about different flavors of quantum biology. And for the next talk, please read the chapter called Introduction and the chapter called What is Life? Okay, so even if you're not an undergraduate at UCLA, you can register. We're going to put the links soon, again, in the chat. You can register to have access to all the discussions that we have in our internal platform here, which is, again, not only open to the UCLA students. There's more than 100 people who signed up for these seminars. They're going to be recorded. We're going to be sharing the place where we're going to put the recordings. They're going to be uploaded to the Quantum Biology Tech Lab, our Qubit Lab at UCLA YouTube channel, okay? But since there's plenty of people in this room already, which is super cool, we're going to try to ask you that the only people that could please pause the speaker during the presentation to ask questions. We're asking that only undergraduates, it doesn't need to be at UCLA, any undergraduates and any high school students, you please feel free to pause the speaker to ask for, to ask questions, but that all of the other people in this room, were already 76 people, all the other people who are not undergraduates or high school students, please leave your questions for the end so that we give the youngers more opportunity to engage with our speaker. This said, feel free to drop your questions on the chat. We are going to try to reply to them, but if you're an undergraduate or a high school student, feel free to unmute yourself and pause Abasalt. With this said, I'm going to give you the screen to Abasalt, who's going to give us a little bit of an introduction on quantum mechanics.
Hi, everyone. Thank you, Clarice, for the introduction. Okay, how should I wait? Give me a second. Sorry. I want to stop my. Do you see my screen? Clarice?
Yes.
Yes.
Okay. Oh, sorry.
You're muted.
Yeah. Now you see it, right? I don't hear you.
Yes. Yeah, we see.
Okay. I guess there is a bit of delay. I don't know why. But if there's any problem, you don't see my slides or you don't see, you don't hear me, please stop me. Yeah, let me know. Okay, welcome everyone. So today I'm going to briefly talk about some cool experiments in quantum mechanics. Maybe I give you a few seconds to understand this, perhaps the classical versus quantum mechanics, like what are the crazy stuff which might happen actually in quantum mechanics. So yeah, maybe take some time to read this stuff, and then I put a kind of border between classic and quantum. Okay, so you should be prepared to actually to hear a lot of crazy stuff in this lecture. But before starting, I would like to tell you a bit about classic and quantum. What is the differences? For example, when we talk about quantum and classical physics, so we are usually talking about objects that their size are here. They are less than a nanometer, like 10⁻⁹ meter. And here we have objects which are, the sizes are more than 10⁹ meter or nanometer. So here we are then mostly talking about atoms or also electrons and kind of things. And classical physics is like coming from Newtonian mechanics, and it can actually work for many things. For example, if you maybe I trust some. Okay, this is the first time I don't know how to clean this now. So, for example, if you have, if this is the Earth, so this is going around Sun. So all these things you can actually explain by classical mechanics, which actually arising from the very famous formula of Newton. So this is the formula. And for example, even like when we are shooting satellites to orbit around the Earth, so the whole like complicated stuff, like at these scales, we are all dealing with classical physics. Basically, whatever you can see, like in terms of wavelengths or frequency, if we talk, whatever you see, you can actually explain by classical mechanics. But today we want to talk more about quantum mechanics. And why we want to talk about quantum mechanics? Because there were actually several stuff in the history of physics that physicists they could not explain by classical mechanics. For example, I am giving a few examples of failure of the classical mechanics, so you understand that why actually we need quantum mechanics. If you imagine, for example, this is a hot plate, and if you heat it up, so this will radiate at like a yellow or orange color. So this means that it is radiating this wavelengths. So if we talk about, like, if we consider, we want to explain actually these phenomena by classical physics. So if you plot, for example, if you have the wave length, and also you have the energy, if you want to plot it according to the classical mechanics, actually you should get something like this, which means that when your temperature is increasing, so then the wavelength is also decreasing, and then you are getting most of energy at UV area. But as we know, this is not true. Otherwise, we would be cooked by UV light, because this means that when you keep increasing the temperature, then the more radiation you get, it will be at the UV. But this is actually by classical mechanics explained like this, and this is actually wrong. So the proper picture of this actually it should be something like this. So it comes here and then it goes down. So for example, the spectrum that from the sun, if you get the spectrum from the sun, so it will be something like this. So here was the point that actually classical mechanics could not explain, because according to classical mechanics, it should go higher and higher at the energies, but quantum mechanics predicted it very well that actually it should decrease here. So this is one of the failures of the classical mechanics that could not explain. And the other thing that classical mechanics could not explain is the photoelectric effect. For example, if you imagine that there are photons like light, you can imagine monochromatic light coming and heating the surface of a metal, then there are electrons here, and so these waves can have enough energy to eject electron from the surface of this metal. So in classical mechanics, we assume that actually wave is continuous. It can take like a continuous energy. So this means that if you want, for example, to eject one electron here, there will be actually time delay between shining the light and then electron being ejected. But we know that actually, if you perform this experiment, you know that actually this effect is very instantaneous. So there is no time delay between like shining and ejecting the electron. And so like this is one of the also experiments that classical mechanics could not explain, and we'll go through that in quantum, and we'll explain why this is happening. The other thing that in classical mechanics is not able to explain is the stability of atom, because according to the classical mechanics, you have the nucleus of the atom here, and then electrons are orbiting around the nucleus. And according to classical mechanics, we know that if you have a charged particle and they are in motion, they will radiate energy. So if electron here is radiating energy, this means that it is actually losing energy. So over time, what you should expect is that this orbit goes smaller and smaller, and finally it should crash the nucleus. But we know that this is not happening. If this was actually true, then in 10 to the minus 12 seconds, actually, you would have no atoms, basically, because the electron would very fast fall into the nucleus. But this is not really happening. So bringing these examples, I want to give you some introduction about quantum mechanics. And here I am just presenting few experiments in quantum mechanics done by great scientists. I will start with Young, who actually performed a very cool experiment in 1801. So let's perhaps do the experiment together. I will explain the experiment, how it will be, and then perhaps you can have like some time to think about what do you expect from this experiment. So if I give you a monochromatic light source here, and then it is radiating monochromatic light, okay, and then you have a curtain here, and then there is two slits here. So this light is coming and hitting the curtain, and then after this you will have the second like a detection curtain. So if you have two slits here and you shine this laser light, so the question is, what do you expect to see on the curtain? So do you expect that you see like two bright spots, like depending on the, of course, the wavelengths of your wave, or what else? Can you imagine like what you would expect? So this is something that actually Young did in 1801, and it's a very cool experiment. So very surprisingly, what you will get is something like this. So if you have your light source, and then you have the first curtain, so that you are filtering out the wavelengths, then you have a monochromatic source, like unique source of the light, and then you have two other slits here. So this is the top view, basically. So you have two other slits, and then you see that each of these slits, they actually themselves, they can behave like a light source. And then if they behave like a light source, and if you imagine that actually light is wave, then what you see is these waves can go and interfere with each other. So here, what is happening here is a diffraction, which is a kind of bending light or spreading light over edges. And then what is happening here is the interference of these two waves, which means that, for example, if you have one wave and like coming this way and the other way coming this way, but they have opposite amplitudes, then they will actually cancel each other. So you will have a flat line. So here, what you see here, like as a dark spot here, this is the destructive interference, and these bright spots are the constructive interference. And depending on the wavelengths of your light source, or let's say the color of your light source, the bandwidth, this size of this can be different. For example, if you shine a green light, this will not be the same as red light. So this is the basic idea that Young did, and with this later on also Maxwell came, and then with Maxwell equations, so we closed up this discussion that okay, light is wave. And if you want to perform this experiment at home, it can be actually, it is very simple. If you have, I have done it several times back in Germany, because once a year we were actually giving a science fair to children, and then I actually used a very simple comb like this and the laser pointer, and then I got something like this as interference. So what you do basically, if you have a comb like this, which is easy to find, and the distance between these lines are like, I would say less than a millimeter, and then you put two tapes, two black tapes, and then you have a kind of double slit here. And then if you shine this laser beam, if inside it is also big and it covers here, so if you shine through this, on the far away on the wall or on a screen, you will see this beautiful pattern, which this way you are actually proving that light is wave. So this was a big discussion among physicists that what is really light. So we had no understanding of light. So this was one of the first experiments performed to understand it. But we talked about light, but this experiment is even cooler than that, because if you have the same curtain with these two slits, and this is the detection curtain. So what if instead of light, I shine, let's say electrons, I shoot electrons. So then I shoot lots of electrons, and then they go through the slits. And very interestingly, you will get the same results, which means that instead of having two bright lines behind this, you will actually get interference pattern like this. So this means that so this wave property is not just limited to light, also particles like electrons or neutrons or atoms, they can also behave same. So you can also expand this. You can also expand this concept that, okay, if electron behaves the same, then I can also consider that the matter also will behave the same. For example, if you put, I don't know, a very small object here, it should also like behave the same, and then we will come to that point. So even more interestingly, here you are shooting a lot of electrons here, but I can tell you something else, that if you have just one electron, and then you shine it through this two slits, again you will get the same interference patterns. What does it mean? It means that this electron comes, and then actually here electron doesn't know where to go. So then it decides to go on the right or the left side. So actually it goes through both of them, which means that electron is actually like a wave. So it goes through both of them. And behind this, you will have two waves like this, and then they interfere like this. So then it doesn't matter if you have a bunch of electrons or just one electron. So you will have the same interference patterns. Again, we are proving that okay, light or matter, in generally speaking, macroscopic matters, they can also behave like waves. Okay, he is saying that, how about, for example, human beings? So I gave you an example of comb, for example, you can do at home, double Young experiment. So what if you stay right beside these double slits? So what do you expect? Do you also expect that you will see interference patterns on the curtain? Actually, the answer is yes, but there is a condition for this experiment, and the condition is the size of this slit should be comparable to the wavelengths of your your body. So this means that if you stay behind this double slit, so you need a slit size. So the slit size should be 10 to the minus 6 meter. Imagine how small it is, and I guess we cannot actually produce this very small slits. But if somehow you can produce this slit, and you are here behind the double slit curtain, then you will also see the interference pattern behind, again proving that the matter also can behave like a wave. Oh, wave. Yeah. But I can also give you like just if you want to understand like how small this size is. If you scale up one atom, like one atom has a nucleus and an electron. If you scale up to solar system, so this is sun, and then this is the Earth, then the size of the wave packet of the human being can be as the size of one atom. So then imagine that like your size will be one atom in a solar system. So that's super small. That's why actually in a daily life basis, you don't see effects of wave properties of your body, for example. Okay, the next experiment I want to explain is a photoelectric effect. So I would like to draw you this experiment, and then again, you can think, what do you expect? So if you have a metal, and then we have electrons here. So what I am doing, I will shine a monochromatic light again. And then I am expecting that, so this has been experimentally proven that then you can eject electrons, okay? So the question is, what do you think if I increase the intensity of light? If I increase the intensity of light, what do you expect? Do you expect that you will eject more electrons? Or do you expect that you will eject, for example, faster electrons? Velocity will go higher? So this is the question. People did actually this experiment, and very surprisingly, it seems that actually it doesn't matter to the intensity of light. So what matters here is the frequency of light. So frequency we show by F or no, something like this. So which means that this electron, even if, for example, you have a dim light, but it has the threshold frequency, then you can eject electrons. So basically, if I want to plot this, so it should look like something like it. So if this is your frequency and this is the energy of the electron, so you have to have something like threshold frequency. So you keep increasing your frequency until a certain point, and then afterwards you keep exciting the electron, so ejecting the electron. And so the energy that you are giving, it is actually it will be spent to eject the electron plus accelerating it, like giving it kinetic energy. So the kinetic energy of the electron, so the energy that you are giving, the kinetic energy will be equal to energy that you gave minus the energy that you have to actually overcome to eject the electron. Okay, so and this from quantum mechanics, we know that this energy is just depending on, as I said, to the frequency. So it is just one constant times the frequency of the light, and this is the Planck constant, and this is very, very quantum. This is you have to remember this. So in the experiment, it looks like this. So you shine some light here. You have two metals, one is anode and a cathode. They are connected to a voltage and also ampere meter to measure the current. So what you do, you apply some voltage here, okay, in the anode and cathode. So there is a voltage difference, and then you shine your laser light. So it has if it has a certain frequency, then it can eject the electron, and then electrons can be accelerated because there is a voltage, so it can be accelerated into this tube. So what you can do here, if you want to measure the kinetic energy of the electron, you can actually tweak this voltage, which means that you apply like opposite voltage to stop the electron until you see no current. Because if there is electrons ejected, there will be current. So you apply negative voltage, and so you don't see any more current. Then the kinetic energy will be also equal to voltage times charge of the particle, which here is electron. Okay. So here we see that we saw two experiments. That one actually was somehow showing that the light can behave like a particle, which was the photoelectric effect of the Albert Einstein, and the other one was from a double Young experiment that showed that actually particle or light can behave like a wave. Here was actually a very delicate time at that time. So because physicists they didn't understand. So what is really light or particle? So they are wave or particle. Here was the moment that actually the concept of wave particle duality came, which means that light can behave like a particle or wave at the same time, like sometimes like a wave, sometimes like a particle, or sometimes as both of them together, like a wave packet. So if you imagine, so this is a wave, and then this is a particle, but you can actually have both of them at the same time, something like a wave packet. This is for example wave packet of the light, and it's called photon, for the first time introduced by Albert Einstein. So now let's go to black body radiation, and we talk about Planck's law. So before going there, so I would like to tell you what is the black body. So a black body, if you imagine that you have a kavak like this, and then there is a hole. So the light which comes in goes inside, so it will be reflected so many times inside. So there is basically no chance to get out of this hole. So the hole is very small. So black body is an object that can emit at almost like all the frequencies. So examples of black body radiation can be this kavak, can be, for example, our sun or stars. For example, if you look at most of the stars, they look like they are red. If you look at the sun has more temperature, so it looks more yellowish. So this is the black body radiation spectrum. So at that time, at the 1900, it was known as ultraviolet catastrophe, because the classical physics could actually predict this area, but actually it was predicting that this will go higher and higher when you decrease the wavelengths, which means that if you go to higher frequencies, then you will have a lot of UV light. So this will keep increasing. But this was actually from like nature. We knew that this is strong, and we could not really understand why this is happening and why we cannot explain this by classical mechanics. So one of the main important things that in classical mechanics we assumed was the fact that the wave or like energy can take any continuous value. So there is no discrete value to assign to energy. But Planck solved this ultraviolet catastrophe with the fact that he assumed that what if we consider that energy cannot be anything like continuous? What if energy is discrete? Then he proposed that what if energy is multiplications of h nu? So this is the frequency, this is the Planck constant, and this is just a number. So what if energy is actually multiplications of this discrete value? Then with these statistics, you see that Planck could explain this black body radiation very nicely. So it could predict this area. And this worked. So he postulated that, meaning that there was no experiment done to prove this that time. So he assumed that if the energy is discrete, then you can explain this spectrum. And this is the spectrum formula, just for you to understand. The lambda is the wavelength, h is just one constant, c is velocity of light, t is the temperature, k is Boltzmann constant. So you see that if you increase the temperature, so our sun has something like more than 6,000 Kelvin. So you see that when you go to higher temperatures, like about 6,000, 7,000, so most of the frequency that you are emitting is at visible light. So that's why we see our sun like somewhere here, which is yellowish or reddish. And most of the stars, because they are cooler, they look reddish. Also, they have like a red shift, but it's a different story. So this was the problem by ultraviolet catastrophe that Planck could solve it. Now, what if you go to Heisenberg uncertainty principle? So here I am just mentioning like a few very cool experiments just to engage you with quantum mechanics. So here also I want to kind of design an experiment. So imagine that again, I give you a light source. So, and then far away, there's the curtain. And there is a slit, but this slit is very big, okay? And then there is this observation curtain, okay? So if you shine this light, imagine that, okay, the light is yellow. So what you see on the curtain, you more or less see the shape of the slit. Slit is very big, okay? Now, if I ask you, what if you keep decreasing the size of this slit? For example, you make it smaller and smaller like this. So you see that the size of this also gets smaller and smaller, but there is a moment that you cannot anymore detect the position of this. So light here gets also narrow and narrow until the moment that actually it expands. And then you don't know actually, you cannot recognize this shape anymore. So what is this? This is exactly the uncertainty principle. What does it mean? It means that if you want to measure the position of something very precisely, then you will be very uncertain about the momentum. What is momentum? Momentum is just multiplication of mass and velocity, okay? So in this previous example, you see that you are decreasing the size of the width of the slit, okay? What does it mean? It means that you are decreasing this, right? You are decreasing this. So what does it happen? It means that the uncertainty in the velocity goes higher and higher. So in another word, in this slit, when the photons are exiting this slit, so they are not anymore, they don't anymore have like a certain velocity, but rather they have different velocities going around, and then it gets blurry and blurry. So this is the principle of uncertainty of Heisenberg. So which means that if you want, so you can actually have any two correlated parameters. Here I am just talking about position and the momentum. And this is actually intrinsic about the nature. So you can never know exactly the position or speed of an object simultaneously. So if you get precise in one, you will lose the other one. So for example, if you have 100% precision in the position, then you are actually 100% wrong in the momentum of the object. So talking about Heisenberg uncertainty, I guess it's good to also talk about the Schrödinger thought experiment.
Yes.
Excuse me. Yes, sir. I have a doubt. So in the previous example, what if there is a detector in front of slit? Yeah, we are decreasing the slit along at the same time we have some detector in front of the slit. So what happens?
So if you perform this experiment, what's going to happen? So you have this size. So if you imagine that you put I guess if you put a lens, okay, and then you have you are collecting all the lights in the photodiode. I guess you will measure probably the same intensity, but the intensity actually will decrease again because anyway you are blocking the light, you know. So if I plot something like intensity versus the size, so I don't know how the relation will be, but for sure if you go down.
But if we put detector in front of the slit, I think like do uncertainty relations still hold?
Ah, you mean in front here?
Yeah. Yes. I mean, like when we observe any phenomena that wave nature collapses, right? But still the uncertainty relations will hold.
So
And
yeah. So yes. Yes, yes.
Oh.
This is a very macroscopic experiment just to understand or digest the uncertainty principle. But otherwise, uncertainty principle is a really fundamental thing, like down to electron. You know, so it doesn't matter what you do, so it is always there. So, but here, if you want to talk about the uncertainty here, so what are your parameters? For example, I talked about the position and the momentum. So you can also talk about energy and time, for example. It can be energy or time. And then they all hold the same thing, you know. As I said, you have to find the two correlated parameters. Yes, uncertainty holds, no, here.
Thank you, Professor.
No problem. Okay, now talking about the Schrödinger cat. What is this? So again, this is very, very, very interesting and actually very fundamental, perhaps crazy also to understand. Because maybe after this experiment you will understand. So imagine that you have a cat and this cat is inside the box. So maybe I draw a very beautiful box for him. Okay, like this box. And then the box is totally closed. You have no idea if the cat is alive or dead. And then there is like radioactive atom. So once it radiates, there is a detector, and then this detector shoots some venom or gas that kills the cat. Okay. Now the question is, with having the whole situation, considering the whole situation, if I ask you, if the cat is alive or dead, what will be your answer? Okay, some of you might answer that, okay, the cat is alive. Some of you might answer that the cat is dead. Okay, but actually, the cat can be. So if I write cat, can be actually the state of the cat, or like status of the cat can be both alive, 50%, plus 50% dead. And this is one of the fundamentals in quantum mechanics. This is called superposition. For example, well, I just wanted to write this cat here now. So superposition, what does it mean? For example, if you imagine that, for example, there is an atom, and then this atom has so different layers with electrons. Okay. If you, for example, talk about also quantum computing and stuff, so this superposition means that, for example, the state, like it generally, like, for example, this is the wave function. So we don't know what is the status of the wave function, for example, wave function of this this electron, perhaps. So then this can be multiplications of a lot of states. Let's call them like this. So I am just summing them up. So it can be like many, right? Okay. So and how do we know that? For example, what is the status of this wave function or state of this wave function? You have to do the measurement. What is the measurement? For example, if you consider this experiment about the cat and box, what was the measurement? The measurement is opening the box, and then at least one photon comes and arrives to your eye, and then you know that the cat is alive or dead. So what does it say? So it means that before measurement, actually you have all these states before the measurement. Okay, but as soon as you measure, the wave function collapses in one of these, let's call substate. For example, in the case of cat, the cat had the status alive or dead. Okay. But how do you know if the cat is alive or dead? You open the box, and as soon as you open the box, this wave function of the cat collapses into alive or either dead. So here is also the same thing. So I don't know, for example, what is my quantum state as soon as I measure it, which means that for example, measurement can be observing or manipulating by laser light and so on. Then I know about the status, and the wave function collapses. This is called observation. So yeah, very briefly also talking about Bell theorem. This is about entanglement. For example, if you have two particles and they are entangled, so first of all, each of them, they are separated system. So we are not talking about, for example, yeah, two systems in one ensemble. So system 1, system 2, they are entangled, which means that both of them, they have same properties. For example, here, if we talk about the spin of the atom, the spin of electron, for example, can be up or down. But here I have no idea if it is up and down, or here neither. Okay. So now the thing is, as soon as I measure one of them, I know that the other one, what is the spin of the other one? If I notice that the first one is red, or let's call spin up, then simultaneously I know that the other one is spin down, or vice versa. So if I know this is spin down, the other one will be spin off. So this concept is called entanglement, and it's actually very crazy. And there are several experiments. Einstein also calls this as a spooky action because it's very difficult to understand. So what does it mean? It means that so if you, for example, if you separate these particles far away from each other, imagine that one is in our solar system, the other one is in Alpha Centauri. So as soon as I measure this and I know that this spin is up, I also know that this spin is down. Okay. Does it mean that actually this information is going faster than the speed of light? Or not? So this was the big discussion among physicists, and Einstein believed that there is somehow hidden variables in between here, so that the particles actually, they can talk to each other. He couldn't understand that how you can actually notice that this, if you measure this, how do you know that this is spin down a bit faster than the speed of light? So there was a guy named Bell, and then he proposed some thought experiment. For example, Alice and Bob. So this is a thought experiment. So they had one detector 1 and 2, and then they measured, for example, one quantity at different angles, and at the end, he concluded that there is not such a thing like hidden variable, or they don't like talk to each other. You know, they cannot talk to each other. So this concept is also called entanglement, which is very important in quantum mechanics to understand. But what are the applications of quantum in daily life? We have actually so many applications. You might know some of them. For example, we have electron microscopy. You can have atomic clocks, which are very precise. You can the advent of lasers, NMR machines, which are magnetic resonance microscopy. Or you have transistors, which is the building blocks of computers. Nowadays, you have quantum computers also. You have solar cells, which are actually working based on the photoelectric effect of Einstein. You have computers. And one of the things which is also interesting is called quantum campus. So maybe I talk briefly about this. What does it mean? So it was also a big question for scientists for years, that how a bird can actually migrate. For example, the name of this bird is robin, and then it can migrate for thousands of kilometers, but it was always a question how this is happening. So until recently, that we have actually kind of quantum-based theory, which is explaining that actually these birds, they can feel the Earth's magnetic field. So the magnetic field of the Earth is about 50 microtesla. Imagine. So this is very small magnetic field. So this bird in the eye has a protein called cryptochrome, and this cryptochrome can actually react with the blue light or green light, for example. And then when it reacts with this blue or green light, it will be photochemically, then you will have two products, which one of them, they are in singlet spin state, and then the other one is triplet spin state. So you don't need really to understand this, but you can imagine that there is two states, okay? This chemical, this makes a reaction with the light, this light, and then you will have two products, and these two products, they are interchanging very fast, okay? Now, if these products, you expose them to the magnetic field of the Earth, which is about 50 microtesla, what's gonna happen? They react to the magnetic field, and then either you end up here or you end up here, okay? And then with this process, the bird actually can see the magnetic field. So if you imagine that this is Earth, so the bird actually, and they are the lines of magnetic field. So what is happening is actually this bird is seeing these lines by the eye. So this is called quantum campus. And this is one of the reasons like why we are very interested in quantum biology at UCLA. So we are designing microscopes that are equipped to magnetic field coils, and we are going to apply magnetic fields. And we want to understand that if by applying the magnetic field, for example, up to tens of millitesla, if we can actually change the direction of chemical reaction. This is very cool. Imagine that, for example, you get a cancer. How do you get a cancer? Some cells, they don't, like you have some, I don't know, some chemical reactions, and then this escalates and then ends up with lots of cells, then they migrate to the rest of the body. So actually, we know that nowadays with the effect of weak magnetic fields, can be static or oscillating magnetic field, you can have a lot of effects at the cellular level. For example, you can stop the migration of the cell because cells, they migrate. For example, when you have injuries, for the wound healing, the cells, they migrate and then they cover this wound, so you heal. So with the magnetic field, you can alter this, you can stop it, or you can speed up this process, or you can alter the morphology of the cells and lots of things. So we want to, with our microscopes, we want to understand the spin-dependent chemical reactions. So basically, we want to expose protein, let's say, for example, cryptochrome protein, to the magnetic field, oscillating magnetic field, or DC magnetic field, and then looking at the fluorescence of the this protein, if it is changing or not, you know. And in the future, of course, it has a lot of applications, especially in medicine, I would say. Okay. So,
sir, excuse me,
yeah.
Sir, can you kindly explain once again explain the working relationship of the protein?
So, so it is known that the birds in the eye, in the retina, they have a protein called cryptochrome, especially cryptochrome 4. And I've heard that actually, like almost every cell, they have this protein called cryptochrome. Okay. So this cryptochrome protein is very light sensitive. So, and it's only sensitive to like something like in between of these two. Okay. There are many experiments that they have done this experiment by, let's say, red light, or like below or over this wavelengths, and they see no effect. So this cryptochrome protein, it can react with this light, and then at the end, by the reaction, you will get two products. Okay. These products, they are quantum mechanics products. Why? Because we are talking now about the spin. When we are talking about the spin of the for example, electron, we are talking about quantum mechanics. So you see that this bird somehow is using, let's say, quantum mechanics to find the direction, to orient itself. So if you have these two products, they are interchanging in interconversion, like very fast. So they are oscillating between these two products. Okay, between these two products. And then when you expose them to the magnetic field of the Earth, which is actually very small, weak magnetic field, then they end up here or here. Then at the end, so with like population in this state, the bird actually can realize, for example, if the magnetic field is north or south, you know, the direction of the magnetic field, and then can migrate, for example, from here to here, yeah, from north to south. So these birds are called robin, yeah, and it is very well known and well studied.
So magnetic field is changing the probabilities, is it right? Like
exactly.
Okay.
Yeah, magnetic. So this is called radical in physics. It is called radical pair mechanism, and this radical pair mechanism is also working with this magnetic field. So the magnetic field can affect this exactly, and then you will end up, for example, in this cryptochrome, you will end up with, for example, more or less in this state, you know.
Yes, Professor. Thank you. Got it.
Yeah, this is one of the examples. Of course, we have also other animals like turtles or like even big whales and so on. So they also somehow, they can also orient themselves. We still don't know exactly how they can actually orient themselves. But about birds, this radical pair mechanism works very well apparently. And there have been a lot of studies. For example, So what if you cancel out this magnetic field? There are many experiments that if you actually cancel out this magnetic field, the bird will be lost. So so they put the bird into a funnel, and then they apply, for example, zero magnet, like there is no magnetic field. They cancel the magnetic field, and then you see that the bird is lost. Or what if, for example, they shine a red light instead of green or blue light? They see that the bird is lost. So the bird can only orient itself if if it sees these two, like these frequencies, and then something like this magnetic field. Yeah. So maybe the father of quantum biology would be Erwin Schrödinger, because he was the first one actually that he wrote the book What is Life, and then he said that the macroscopic order of life was based on order at its quantum level. So yeah, I think I call him a father of quantum biology, as I find him the first one who says this. And a bit of background about my experience and how I became a quantum physicist. I started my education back in Iran. I did my bachelor there, and then I moved to Brazil. I did my master in experimental quantum physics. Then I moved to Japan, and then I studied theoretical quantum physics. Then I did my PhD in Germany in atom-ion quantum experiment, which I actually designed an experiment which we could trap two different species of atoms and then study the interaction of them. Then I got back to Brazil because I had no biology experiences, and then I spent 6 months at the Heart Institute back in Brazil, and then I gained some knowledge, and then I moved to UCLA a few weeks ago. So where I'm currently working. So with this, I would like to end my talk, and of course, if you have any questions, it is welcome.
We're good. Questions, everyone. And anyone is open to ask questions to Abasalt or to any of us here. Where's Abasalt?
I am here. Because I still on my iPad.
Oh, okay. What are your questions?
Could you guys recommend some materials to review more basic quantum mechanics topics?
There are lots of textbooks out there. I don't know really which one to suggest here, but for sure, for example, I would suggest that if you want to really understand physics, like my favorite physicist is Richard Feynman, and you can find his lectures online, all available.
Abasalt, you have a question from Hama.
Yes.
What's your personal interpretation of spin in the context of biology?
Well, I mean, my personal interpretation of the spin itself, it is very difficult thing to understand. I really don't understand what is the spin. So I know the spin by, for example, manipulating them, by how they react, for example, in the experiment, how I can manipulate them, how they answer to what I do. But if you really want me to explain what is spin, I cannot do that. So it's something that, sorry?
Go for it.
Yeah, it's something that, for example, for me, spin is a black box that I interact with it. And then I know that, okay, I can have a spin up, I can have a spin down, and I can have, like, I can measure the probabilities if you measure lots of them. So it's something that I am interacting, and then I get information by the interaction.
Can I try? Okay,
sure.
So here's how I view spin, right? So, spin is a fundamental property of matter that is as fundamental as charge and mass. And if you think about it, right, we all understand what mass is. Mass is the thing that we use to describe how objects interact with the gravitational fields, and we call charge the property that mediates how objects interact with electric fields. For example, charge can be positive or negative. And we all know from high school that things that have positive charge interact with electric fields in different ways with things from negative charge. So I like to think of spin as the same abstraction for how objects interact with magnetic fields. In the same way the charge can be positive or negative, people usually represent spins with an arrow. Arrow up or arrow down signify different ways that this object interacts with magnetic fields. So in the same way that you can have a positive charge and like electrons have negative charge, but they're like ions that have positive charge and they interact differently with electric fields. If an electron has a spin up, it interacts differently with a magnetic field if it has a spin down. So this is one way that I like to think about spins. Again, it's an abstraction in the same way that charge and mass are also abstractions, if you will.
I think there was another question for you, Abasalt, and it was from Susie. Could you explain black bodies again? How is the sun akin to that object you showed on your slides?
Should I show the slide again, or? So what is the exact question, Alessandro, again?
If you can just briefly go over the black body again and how,
Sure.
How it's similar to the sun, I guess.
Okay, sun is also kind of, let me see if I am, do you see my screen now?
Yeah.
Okay, so if you look at this, you see that, I can, that's okay. So you see color of sun is mostly yellow, right? Yellow or reddish, right? So, if you increase the temperature, you see that here, I am increasing the temperature of the object. So the sun also has a certain temperature, right? So you're increasing the temperature, and then sun has like something like this temperature, about 7,000, okay? And that's why it is radiating this spectrum of light. So mostly in the visible light. So this is, you see that maximum frequency that the sun is radiating is at frequency at visible light. So sun is a black body. It can be as a black body radiator, because it is actually radiating. You see that it is radiating all these frequencies. Okay, as I said, the black body is object that can radiate all the frequencies. Okay, so any object, for example, even if like an oven in your that you have at home. So if you increase the temperature, the oven at some moment, like the elements, okay, they start to radiate in red. So what does it mean? It means that the temperature is actually reaching somewhere here, you see, and then it is radiating this frequency. I don't know if I answered the question.
Okay, then I'm gonna just throw the questions at you.
Yeah.
Then we have a question, which is, could you give an example of the way in which some of these formulas are used in biology, or the mechanism in biological instruments through some of the formulas you mentioned?
I didn't mention actually so many formulas. I guess this is the only formula, but let me see. Okay, I have to look which kind of formula did I say? Okay. Okay, for example, maybe we talk about these applications in quantum mechanics. So they are all using the fundamental quantum mechanics. For example, when you talk about this electron microscopy, how it is working, it is based on quantum. So it is electron tunneling. In biology. So in biology, we have this bird, and then, as I said, the bird can have this singlet or triplet state at the end because it is reacting with the light, and then these two states, they are the spin state. Okay, this is the quantum concept, and then they react with the magnetic field that was about 50 microtesla, and then they end up with one of these states. Yeah, I would say that, yeah, the only formalism that I know in biology that we use a lot is radical pair mechanism. But of course, you know, if you really want to study biology by physics, there are lots of things. For example, if you go to, for example, one cell, so I don't know too much biology, but I can explain a bit. For example, if this is a cell, there are these ion channels here, so the ions can go through or can back and forth, like inward or outward. So if you apply magnetic field, then you can actually alter the flux of ion through the ion channel. So this is a very basic like physics, not necessarily quantum physics. But if you have a charged particle, for example, with charge Q, and then if you apply the magnetic field, like in, for example, like this, then the force, for example, the force which is exerted to this charge will be multiplication of charge times velocity times the magnetic field, which means that if you have this particle moving in this direction, then with this magnetic field, so you have outward force. So yeah, you can study lots of things with physics, like in biology, you can study many things. So I'm just thinking, what else? Clarice, do you remember any other examples? That's physics formalism and biology.
Abasalt, can you hear us?
Yes, I was lost. Sorry.
No, we were lost, I think.
We were lost. Yeah, one of.
Yeah, I was explaining that, for example, this ion channels, for example, you can also like analyze them by rules of physics. You know, it's like really basic Lorentz force, for example. And then if you apply magnetic field, oscillating magnetic field, or DC magnetic field, you can actually alter these kind of things. And if you alter the, for example, the ion flux, you basically alter the metabolism of the cell. So everything actually changes. So maybe you can, if you have, imagine that you have a cancer cell, and then just by this alteration of the ions going inward or outward, you can actually maybe kill the cancer cell, you know. But in our experiment, we are going to design these microscopes that basically we will apply the magnetic field, and then we will study the spin-dependent chemical reactions. So when we are talking about the spin, as I said, so we are talking about quantum physics. So for example, coming from bird, so we know that now bird can actually react to the magnetic field of the Earth. Why? Because it has this spin-dependent chemicals inside. So we can have the same stuff like in many things actually. Question?
May I comment? May I comment a bit on the relevance of electrical charges in cells?
Sure.
Okay, so well, my name is One Pagan. I live in Pennsylvania, and I'm from Puerto Rico. Go figure. But the idea is that for any type of cell, let's go back, for example, in our world, it's built upon electricity. We use electricity for everything, but the biological world depends on the distribution of charges in and out of the cell too. And this is for the benefit of the students that are out there. So if we, as you said very well yourself, when you change the distribution of charges in and out of the cell, you can fundamentally alter the properties of the cell. And we're talking about cancer biology. We can talk development, muscles, cells, nervous system interaction, all these type of things. And I saw a very interesting question about pharmaceuticals in there. That's a very important consideration because we can have medications that can be agonist or antagonist that can enhance or inhibit a particular cell function, which may be due to quantum mechanical properties of the small differences in the structure of a molecule. And I'll stop talking because if I will never stop. But it was a great presentation, and I'm having so much fun with you. Thank you for the invitation.
Thank you so much. Actually, what you mentioned, it is actually very great. It was a very great point, because one of the goals that we have in mind is, for example, with the microscopes that we are going to design, is one of the goals is actually we might actually decrease the side effects of the medicines. Maybe you are actually giving too much dose, but if you apply, for example, magnetic field, and then you have this spin-dependent chemical reactions, you might not need actually that much of doses, And this is one of the things you very nicely you mentioned, and yeah, we are also on that.
We are talking in pharmacological terms about the affinity of a drug towards its target. It makes it stick better, quote unquote, or worse.
Yeah.
And now I'll stop, I promise.
Yes, you're right. Yes, you're right. And this field has not been studied actually. And it's very interesting because nobody really, I wouldn't say nobody, but many people actually don't believe that there is quantum effects in biology, but we strongly believe, and there are some evidences. And what you mentioned, it was very nice and very interesting, of course. And we hope that one day, yeah, we can actually manipulate these things by magnetic field and totally based on quantum physics. Thank you.
Hello, may I say something? Hello?
Yes, sure.
Hi, so I wanted to add 2 points. One regarding what Abasalt and Dr. Clary said. So the question regarding how to use spin in quantum mechanics. So back when I was an undergraduate in my first year, so I used to think, not in my first year, as a matter of fact, when I started learning physics and charges itself. So I used to always ask this question of how charges or these basic quantities, how can we interpret them in terms of very basic ideas. And so there are some symmetries in nature that exist. And I would like to point out that because of those symmetries, these things pop up. And I mean, there are undergraduates here, so I'm just saying that. So so because of these symmetries, these things are coming into being. And so when you think about it, if you ask the question, why there is charge itself, what is negative and positive charge, why is there spin? So there are certain fundamental symmetries in physics, which are the most fundamental reasons of why you can have this charge and spin and other things. And the second point that I wanted to add was, Dr. Clarice mentioned about Heisenberg and Schrodinger and Feynman being not very good people. So I took a course in social theory, and so I used to always admire scientists when I was very young, and I used to have this picture about them, which was actually made up in my own head. So I read very moving articles about Schrodinger and his view. I mean, he had very sexist views and other things, and Feynman as well. And so I realized that. So what I was thinking about them was in my head. So I was building a character, and I was building some role model for myself. But that was my own imagination. So whenever I look at any physicist's work or any scientist's work, I always view the work itself rather than how they were as a person. I mean, there's no guarantee that the person was she or they were good people. It was not necessary. So one should just view the work as something. I mean, they should be inspired by the work, but not build ideas about people from what they do. Thank you.
Thank you for the comment.
To end, go for it, Natsumi. Go for it. No, go for it. One of you, I started.
Yeah,
No, he's been
I
talking.
mean,
Are you?
I think if there are no further questions, that's it for today, and we hope to see everybody next week, or I don't remember what topic.
What is
Bye-bye.
life? It's,
What is
Yes.
life?
yes, chapters 1 and 2 on Life on the Edge. Please come having read chapters 1 and 2.
Yes, thank you, Abasalt, and
Thank you, everyone.
see you everybody next week.
Thank
Bye.
you.
See you next week. Bye.
Thank you.
Thank you.
Bye, Anna.
Bye.
It's nice. Very nice.